All right, good afternoon, everyone. Couple quick reminders. So the midterm is going to be on Wednesday. It's a take-home exam for one day. So we'll post it at 10 a.m. On Wednesday, and it'll be due on Thursday at 10 a.m. And so there won't be any class on that day, so that you guys will have more time for your test. Also, for the group project assignments, again, please make sure to reach out to your mentors. I know that some of you have done this already, but not all groups have reached out yet. And the group project abstracts, again, are due on Friday, not on Wednesday. We pushed it back a little bit since it was overlapping with the midterm. Okay. So the couple questions going on here. There's no time limit. You just have to upload before the due time. Yeah, so it's like a 24-hour take-home exam. You can spend as much time as you want on it up until it's due. Yeah, it's not going to be one of those things where we administer it during class and you have to turn on your video. Yeah. There's a question, will there be a review session before Wednesday? Actually, I'm kind of going to be treating half of today's lecture as a review session. I would have had a review session for office hours this morning, but actually no one showed up. But that's okay. We'll cover the practice midterm exam, and then we'll go over any additional review that folks have. And actually, Facundo is just messaging me, and he's saying that he can actually change his office hours for tomorrow from 6 to 8 p.m. So why don't we go ahead and do that, so that there will be an extra review session, and make sure to post that on Canvas, because I guess not everyone's going to be watching the lecture live. Okay, sorry, what was that?
I can make an announcement today.
Yep, great. Another question, for the project abstract, do we need a timeline? Yeah, so I think that would be pretty helpful. I know, yeah, sorry that it's been kind of vague what to put on the abstract, but hopefully those examples will give you a sort of general outline. It doesn't need to be exactly like that. It can be, flexible. Basically, I want to be able to see that you guys have started to give some thought and structure to how you're going to be doing the project, right? And so, don't worry so much about like the grades for the abstract. Worry more that like you are organizing yourself to do the project. And the whole point of the abstract is to like make sure that, it's easy, especially in these times, to procrastinate on these things, but structuring out some of the stuff that you want to do is going to make sure that you keep up to date with working on the project. So that's mainly what I want to see. Some thoughts about what it is that you'd like to do, and maybe some organization and information, probably most ideally in the form of a timeline, for what the schedule of working on the project will look like. How many questions are going to be on the midterm? It's going to be probably just a little bit longer than the practice midterm that we gave. So it's not gonna take 24 hours. Okay. So why don't we get started so that we'll have enough time to cover all of the stuff on the practice midterm. Okay. So we're talking about nuclear energy today. This is kind of our last set of energy technologies that we'll talk about before transitioning to more of the policy emphasis. And so we've talked about fossil energy and we've talked about renewable energy. And today, nuclear energy will be a little bit different from both. So energy can be derived from nuclear reactions in two different ways, nuclear fission and nuclear fusion. And so we really briefly covered this in a previous lecture, but kind of to re-emphasize. So fission is energy released when you take an atom, a large atom with lots of neutrons, a heavy nucleus, and it's split to lighter nuclei. And that releases a tremendous amount of energy. And nuclear fusion is kind of the opposite. So when you fuse nuclei together to form a heavier nucleus, you get a lot of energy released. And so we'll show a little bit more about what this looks like. So nuclear fission reaction. So you essentially shoot a neutron into the nucleus of a specific atom. So in this case, it is a uranium-235 atom, and that splits into fast-moving lighter elements because the larger nuclei is essentially a little bit less stable. So you get this fission happening, and usually you get these byproducts, barium and krypton. And then what ends up happening is you get this sort of chain reaction or controllable chain reaction where the splitting of the uranium-236 leads to the byproducts of barium and krypton. One moment. And so this is a commercially available technology. The chain reaction can be controlled. And then the neutrons that are produced go on to basically fuel further fission reaction. And so this produces a lot of heat, and you use the heat to generate electricity. In a similar vein, which I'll show in a couple slides, as most of your other steam turbines. So thinking about coal or thinking about natural gas, where you have boilers, it's all operating in the same sort of way. Okay, and then you've got nuclear fusion reactions, and so this is an example of a fusion reaction where you have deuterium and tritium, both of which are isotopes of hydrogen. They just have more neutrons. Combine them, and you get a helium atom. It expels a neutron, and you get a whole bunch of energy. So kind of the opposite of fission. I'll be perfectly honest, I don't know a huge amount about fusion. It is currently at the research and development stage. It's been examined, or there's been research being done on fusion for several decades now, but it's nowhere, I would say it's nowhere near sort of commercial viability, right? And so one of the things that you have to think about, which we've been sort of covering in previous lectures, is the theoretical aspect of it, the technical aspect of it, and then the economic aspect of it. And so the theoretical aspect, I think, has been demonstrated. Like, fusion is a real thing. We know that it works. We know we can extract energy from it. And we're currently more trying to develop the technical aspect, being able to develop a technology that can actually be able to do fusion, but also to sustain it and be able to extract energy from it. And it's not sort of a straightforward process, and has yet to be, and the technology has yet to be developed where we can sort of take advantage of fusion in a stable way that we can extract usable energy in a commercial way. And that having been said, even if the technology gets developed, right? So people like to point at nuclear fusion as, or some people like to point at nuclear fusion as a potential, big future for clean energy. The economics is kind of the last phase, right? So even if we do come up with the technology, if it's 100 or 1,000 times more expensive than your comparable wind or solar or even natural gas or coal, no one's really going to want to support it commercially because it wouldn't make sense as an investment. So quite a few hurdles, I think, still for nuclear fusion. So where are we at today with nuclear power? About 1/6 of the world's electricity generation is coming from nuclear. It's about the same as the amount of total hydro. So if we think about how electricity is produced with fossil fuel sources, you're burning the fuel to heat up water, make it into steam, and send it through a turbine. Here, it's considered very low carbon emissions because the way that you heat up the water is through the heat that is released in the fission or theoretically the fusion reaction. But there's no combustion of any kind, so you're not sending anything into the atmosphere. And so definitely there's nuclear waste, and we're going to talk about that in a little bit. But in terms of carbon emissions, it's definitely very negligible, and definitely from a climate change perspective, one of the big options that a lot of people talk about. So to talk a little bit more about the technology, we're not going to go a huge amount into detail here, but there's essentially two types of reactors to know about. So one is a light water reactor, and this set of stuff outside of your containment structure hopefully will look pretty familiar to you guys. This is very similar to the coal boiler, where you have steam going through a turbine to produce electricity that gets cooled with an external source of water, right? And then that gets sent back into this location where the water can be heated up and boiled and sent through the turbine. So one of the things to note is that inside the containment structure, there's actually something kind of interesting going on. You actually have there are a couple closed loops of water, right? And so the cooling water, that, if you remember, is that's the water that is cooling down the steam, which then sort of in turn heats that water up, and that's the stuff that's coming out of the plant. And that water doesn't need to be purified or anything. That could be coming from like a local river, and then they send that through to cool down the heated water. The heated water that's going through the turbine, you do want to make sure is relatively clean, so that you're not degrading the turbine performance or increasing the necessary maintenance. And so that water in the coal case is being directly heated up. But in a nuclear plant, it's getting heated up with a separate closed loop of water. And that's because this water will have a good deal of radiation. That is where that water is the water that's being heated up directly by the control rods undergoing nuclear fission. And so as that water heats up, it heats up this, that's the first closed loop of water. The radioactive water will be heating up the second closed loop of water, which will go through the turbine. Okay, I'll actually speak really quickly about radiation at a nuclear facility. It's actually a pretty big misconception that people think that there's a lot of exposure to radiation. Actually, if I were to go to one place to find the lowest radiation on this planet, it would probably be inside of a nuclear plant. And actually, nuclear plants have lower background radiation than almost anywhere else on Earth. I'm sure there are some caverns somewhere which basically have no radiation, but the safety protocols that they take in modern day nuclear plants are so stringent, and the materials that they use for construction and building are so good at preventing radiation from going through, that nuclear plants actually offer lower background radiation than your natural environments. Okay, breeder reactors, you don't need to know too much about this. I'm kind of just introducing the concept so that you know there's this other sort of reactor that exists. So a breeder reactor is something which generates new fissile material at a greater rate than it consumes. So essentially what that means is you are expelling neutrons that result in the creation of heavy nuclei atoms at a higher rate than you are fissiling that material into smaller into smaller atoms. And so this whole process consumes less uranium, it generates less waste to produce the same amount of energy. But we'll talk a little bit about why you might do sort of one versus the other. But again, we don't need to get so much into understanding the details behind breeder reactors. Just know that these things exist. They're an alternative to the light water reactors. And they create new fissile material as you do the reactions. And then in terms of power cycles, we have what are called open power cycles and closed power cycles for nuclear plants. So in an open cycle, you go through this kind of supply chain. Okay, so we have the uranium mining and milling. It gets converted to uranium hexafluoride and then enriched. You make the fuel, and then that gets sent over into your reactor, right, to do the nuclear fission. Okay, and so both open and closed steps in the supply chain are the same up to this point. And then for the open cycle, you take the spent fuel and you put it into storage, and you in theory, you would put it into a waste repository. And we'll talk about some of the details about that in a little bit. But in a closed cycle, the spent fuel actually still contains material that in theory could be used as a fuel. And so that gets reprocessed. You separate the uranium, and that goes into a different sort of fuel fabrication, and then you can send it through a reactor again. And so this closed cycle is essentially a little bit more quote unquote fuel efficient, and you can use up more of the energy at another nuclear plant. And it does have to be slightly different. The materials are not always the same. So those are sort of your examples of open and closed cycles. So there's definitely, I think, obvious advantages to closed cycles. So you're recycling a lot of the waste. So you essentially need less raw material for the same power output, because I can get more out of it, essentially. In addition, for the same reason, you end up with less radioactive waste needing to be stored for the same amount of energy. But that having been said, it's not super clear that the closed cycle is always preferable. So there's a couple reasons for this. So recycling of the fuel is more expensive than the original uranium. And so thinking about this process here, all of this sort of costs money. And so to the extent where your trade-off in terms of how much it costs to produce the energy and being able to recycle it versus just buying uranium, that can actually lead to favoring the open cycle, especially because there's a lot of uranium at pretty reasonable cost. And so I did mention that long-term waste storage is this issue, and so you're generating more waste with the open cycle. But that having been said, actually the reprocessing and the fuel fabrication of the spent fuel can actually be pretty complicated, and I guess sometimes can be dangerous. And so you are increasing some sort of risks to the environment in that sense. And then there's a pretty big worry that the reprocessing procedure in the closed fuel cycle can actually produce plutonium that can be used for nuclear weapons, which is definitely not like a trivial issue. And so there's a whole bunch of reasons why open cycle, despite it being less efficient, has some pretty compelling reasons why we would pursue that. Okay, technology roadmap for nuclear power. These are basically different generations of nuclear power plants over the last couple decades. Yeah, I'll leave this sort of for reference. We don't need to get so deep into this, and I do want to make sure that we have time for our practice exam. So nuclear power plants capacity is increasing with about 50 reactors under construction worldwide. And we'll look at how this trend has sort of changed and altered over time. So most of the reactors are in Asia, but there's some plans for new units in Russia. In the US, a lot of them are extended, but there's not so many new nuclear power plants being created. And in certain regions of the country, like California, for example, we actually only have one power plant left, and that's due to retire in 2025. And I'll talk a little bit more about that. So worldwide, there's about 450 nuclear power plants in operation. This one's a little bit older. There's some new plants that have come up since this table. So these are different reactor types. We don't need to know details about what these constitute. And then these are the countries where those reactors are located. You can see or primary countries. These aren't the only countries. Like Canada doesn't have 44 nuclear plants. And then the GWE is the gross capacity. So if I added up all of the gigawatts and the capacity of all the 265 pressurized water reactors, that would add up to about 250 gigawatts, which is an absolutely huge amount of energy. Again, your typical like really big coal plants would be maybe 1 to 2 gigawatts. And so nuclear plants are definitely the biggest power plants by far. You can look at the type of fuel that they use. Mostly they're uranium. And then you've got coolants and moderator. So the moderator is part of the reactor units that keeps it's part of the containment structure of the reactor. This is just a view of nuclear reactors by country. You can see in green, so on the right-hand side, each square is a separate power plant, a nuclear power plant, with green being the ones that are operating currently. Red are those that have been shut down, and then purple are units that were in construction and then abandoned. And we'll talk a little bit about the construction woes of nuclear power. It's one of the bigger issues with implementing this sort of on a wide scale. And then orange, you can see, are under construction, with this half orange being behind schedule. And so you can see all the new ones in the US are behind schedule. There's a lot being produced in China, which is mainly where the new power plants are being constructed. And then this graph here, the squares kind of show a similar type of thing, but you can see the timeline of capacity, which is on your y-axis of generators. And you can see which ones are currently operating and which ones are under construction. Okay. But even that can change really, really quickly. So in the recent years, in the last decade, following the big disaster at Fukushima, Japan basically dropped their nuclear generation. They stopped their nuclear plants from operating. And so even though they have some number of reactors, you can see that they're not actually doing anything. In the United States, over 75 reactors have been granted license renewal. So what this means is that the nuclear plants are usually supposed to operate 40 to 50, maybe even at the really long end, 60 years. And essentially what's been happening is instead of building new plants, the licenses are being granted to renew old nuclear plants. So as I was mentioning, there's one nuclear plant that has 2 units operating left in California, and that is the Diablo Canyon nuclear power plant, located near San Luis Obispo. One moment. I need to pause for one quick second. Sorry about that. Okay. Is there a nuclear renaissance? Yeah, so in the 80s and 90s, very few new plants were being built. And then I think a lot of prospects for new construction were starting to increase in the 2000s. And a lot of the sort of biggest producers of electricity, so of nuclear electricity, so US, France, and Japan, were planning to essentially extend a lot of the license and operating lives so that they would be able to maintain their existing nuclear fleet, as well as produce plans for future construction. And so in some places, I think that there's still lots of development for future plants. However, there are a number of countries with pretty strong anti-nuclear lobbies. In particular, so Germany really started moving away from nuclear plants in the last decade. And there's been some criticism that that's leading to more environmental damages, so that means that they were actually relying more on coal plants, but they've sort of since made a really big move to renewable energy, such as solar. And so that has since sort of mitigated a lot of the environmental drawbacks of moving from that sort of temporary moving from nuclear power to coal power. Okay, why the growing interest in nuclear? Policies.
There's a question.
Oh, yes. Do most of these European countries share and export the energy? So with France, yeah, so it's a bit of a complicated answer. With nuclear power in particular, it's hard to sort of ramp it up and down to sort of keep in line with your demand, which changes, which fluctuates a lot from day to day. And so, yeah, I think that that because of that, the nuclear plants are running sort of at full capacity the majority of the time, which means when the demand is low in your particular region, you'll end up exporting a lot of that energy. And so, yes, the short answer is that a good deal of like France's nuclear power plants energy does get exported to other countries. It's a little bit complicated to be able to attribute the electricity to the nuclear plant. So that's kind of a separate issue. But yeah, a lot of the electricity does get exported. So why growing interest in nuclear? One of the biggest reasons is for climate change, right? So global reductions of CO2. This is a technology that can really help out with that. Unlike solar and wind, it doesn't suffer from issues of intermittency. And it's considered something that would be able to serve, the base load of electricity demand pretty well. There has been a slightly more favorable regulatory environment in the US for approving applications, although that statement might be a little bit more controversial. I mean, the regulations are easing up, but they're still fairly they're strict enough, and they're changing enough in ways that construction ends up getting extended a lot of times. There's improvements in the performance of nuclear power plants. So even though it's an old technology, the technology itself is actually still improving for sure, and efficiencies are going up. This slide may be slightly untimely. So rising fossil fuel prices, although more recently, especially this year, we can see that fossil fuel prices have dropped. New generation of power plants were advertised to be safer, more reliable, and cost competitive. Yeah, and so there were, I think, a whole slew of reasons, particularly in the early 2000s, that led to a bigger interest in nuclear and pursuit of construction of new plants. In the last decade, I would say that has, a lot of these reasons have changed a little bit. I think the first one is probably the one that's most relevant, but a lot of these other factors, are in flux. When we look at the IPCC scenarios for 2 degrees increase, which is kind of one of the more optimistic scenarios, basically the amount of nuclear power that we would need, or that a lot of the folks have pointed out in the IPCC that we need, are quite a bit lower than the rate of nuclear plant construction. So that's one thing to sort of keep in mind. And so this is a view of when construction of a nuclear plant has sort of started. And so blue means that it was ultimately completed, green is under construction, and then orange is abandoned. And you can definitely see that there are, both in this chart and the one from previously, there's definitely a lot of this happening where construction ends up getting abandoned. So what are the challenges for nuclear power? You've got basically 4 key issues. So cost, safety, waste management, and nuclear weapons proliferation, which is, so 3 and 4, I think, are fairly different challenges than any of the other ones that we've talked about. I mean, safety too, there are some safety concerns with other power plants, but in sort of a different way. So, we talked more about direct environmental impacts with like pollution, but for nuclear power, we think more of the safety related to the operation of the plant itself. So, okay, there's a question here under the UN NNP, which stands for the Non-Nuclear Proliferation Treaty. Is there specific criteria on who is allowed to build plants? Actually, I'm not sure. I mean, we're going to talk a little bit about the non-nuclear proliferation, but I don't know. I don't actually know the details about allowance of plants. There are definitely countries that have signed on to NNP that have power plants. So there must be some kind of provision, either for grandfathering them in or actually just allowing the nuclear plants. But I don't actually know. Okay. So diving back into the slides, thinking about costs. The costs of nuclear versus fossil energy. So these are levelized costs, right? So over the lifetime, depending on and considering how much electricity is produced, one of the things that you'll notice is that the dark gray bar representing the capital costs is kind of the largest portion of nuclear energy, and that in itself has a lot of uncertainty. Whereas the operations and maintenance, as well as the fuel, is considerably lower than your alternatives. And actually, this is in 2009, which is before the natural gas boom. So actually, the gas costs are quite a bit lower now. And one of the things that was being pointed out in this paper was that, if we include a carbon price, in other words, a way to internalize the emission damages from the generation of electricity, and you were to sort of monetize it, you can actually show that the nuclear plant is lower in cost than coal and gas from an economic standpoint, right? So the tax would increase the cost by this much and this much for coal and gas, whereas it would decrease effectively for nuclear. And so what you would end up seeing is a more economically competitive technology, and maybe that would push forward nuclear power production over fossil generation. Unfortunately, the capital cost of nuclear plants is really quite expensive, 4 times higher than natural gas, twice as high as coal. And one of the interesting points about nuclear plants is that actually the costs have been increasing over time, which is generally the opposite trend that you would expect. And so here, basically showing the average and minimum and maximum investment costs for nuclear plants. One thing to note is that they are, the technology is improving, they are getting bigger, but even when we control for these things, the capital cost is definitely increasing pretty dramatically. And we can see that again here. These are changes in the levelized cost over time. And the nuclear in the blue, you would usually just assume kind of a decrease here, like we can see for solar in orange, nice little decrease like that. And then for solar PV utility, so this is residential solar, this is utility scale solar in yellow, but for most of my nuclear ones in blue, you can see this kind of arcing upwards, in green also arcing upwards, and red also going up. So as capacity has grown over time, we've been seeing that the construction costs of these plants has been going up as well. So why did this happen? There's lots of factors for it. I think this particular, the graph that the study is being derived from, that study in particular was looking at a examination of costs after the 3 Mile Island incident, which was an accident that happened at a reactor in the United States, which we'll see in a second. And following that, a lot of the prices or the costs went up, and that is related to sort of more regulatory requirements and standards for the plants and for the construction. So these end up taking longer and costing more money. Although one of the things is that was seen particularly in the US, but not so much in other countries that had nuclear plants. So the cost didn't rise substantially in France. Yeah, again, sort of just to reiterate, as one of the reasons why the costs are increasing is because the construction time goes up as there's more regulatory requirements and standards, and the longer it takes to build, that adds more to the costs. And so we can see that in terms of reactor age, a lot of the newer reactors are definitely a little bit, or definitely take a longer time to build. Okay, let me see, for purposes of time, I'm gonna skip ahead to our nuclear power safety. I have a couple YouTube videos here that talk a little bit about the incidents, the major nuclear accidents that have happened in the last 50 years or so. So you can look at those on your own time if you're interested. So we'll quickly talk about the incidents. So in Chernobyl in 1986, one of the reactors suffered a massive power excursion, which led to a second explosion. And so what ended up happening is that a large amount of radioactive particulate and gaseous materials were dispersed. The secondary explosion allowed, the first explosion essentially opened up the reactor and allowed oxygen to contact the graphite material, which is in the containment structure of the reactor. And so the graphite, there's a whole bunch of it. It's highly combustible, and it was at really high temperatures. And so when you introduce oxygen into that kind of environment, it's going to react and lead to combustion. And so that secondary chemical explosion basically increased emissions because a lot of the radioactive particles were able to be dispersed via the smoke. So pretty serious impacts. A bunch of plant workers were killed in the explosions, and then the radiation was so severe that it caused cancer cases in regions surrounding Chernobyl, and a lot of the areas had to be permanently evacuated because the radioactive material basically lingers. And so here you can see sort of on the border of Ukraine and Belarus, as well as on the border of Russia, where a lot of the zones have been essentially closed and controlled to prevent people from interacting with the radioactive environment. And so serious, pretty ecological impacts and consequences from this disaster. And actually, radiation from Chernobyl has been measured sort of throughout Europe at different points in time, resulting from weather patterns and deposition patterns. So radiation can be pretty far flung. A different incident that happened in 1979 at 3 Mile Island. So this is actually before Chernobyl happened. So there was equipment failure, and combined with the fact that plant operators weren't able to understand the reactor's condition. So what ended up happening was the cooling water within the reactor essentially led to a partial melting of the fuel rod cladding. So that's the stuff that's surrounding the fuel rod. And that led to a release of radioactive material into the environment. So here there wasn't a catastrophic incident like in Chernobyl. It didn't actually lead to any injuries or deaths. And actually a lot of the radiation that was emitted into the atmosphere was too small to result in direct health effects. And that has been borne out in lots of subsequent studies. And so the 3 Mile Island incident was sort of an unfortunate, safety incident related to the nuclear operation, but didn't lead to any sort of negative outcomes from a health and environmental standpoint. But it did lead to, new regulations and standards being put into place for nuclear power plants. And then I'm sure most of you are at least somewhat familiar with this incident. So a little less than a decade ago in Fukushima, there was a massive earthquake, magnitude 9.0, which is really quite massive, off the coast of Japan, that led to a really deadly tsunami incident. There were tens of thousands of casualties, and all of the nuclear reactors actually, as planned, were shut down. But the tsunami engulfed the entire power plants, the Fukushima power plant. And what ended up happening was the flood destroyed the backup electricity system that was supposed to be powering pumps to cool the nuclear rods. And so a lot of the reactors began to overheat. And what this led to was an increase in pressure, which lowers the water level in the vats where the control rods are heating the water and being cooled. And so that exposed fuel rods to air, and I guess there was some kind of chemical reaction that led to the production of hydrogen, which reacted with oxygen in the air and led to several explosion events, and that allowed for the release of radiation into the atmosphere. So in that incident, this is a map of where the radiation is. And so in 2016, 5 years after the incident, a report suggested that there's going to be around 10,000 additional incidents of cancer due to radiation exposure from Fukushima, and already some of that is being borne out. So we described this sort of nuclear renaissance happening in the early 2000s, but Fukushima, I think, turned a lot of that around. So a lot of countries underwent a review of the Fukushima accident and were sort of looking to their own nuclear reactors, some of which affirmed continuing commitments, but many other countries accelerated the decline in nuclear power, shutting down existing reactors and canceling construction of new ones. In particular, Japan, maybe not so surprisingly, basically all the nuclear reactors were immediately shut down. And so there's still a question of long-term, what are we seeing from the Fukushima incident in the construction of nuclear energy? It's still going on expansion-wise, but I think probably a little bit slower these days. Yeah. So no more nuclear energy for Japan. As I mentioned, basically all the reactors were shut down, but it does have sort of direct consequences. Nuclear energy accounted for about 1/3 of all of the power production in Japan, and so what ends up getting replaced in that case is or what it gets replaced with is natural gas, oil, and coal. So a lot of fossil fuels to offset the nuclear that gets turned off. And so in 2014, Japan actually announced that it would restart some of its nuclear power plants, but this was met with pretty wide-scale disapproval by the public. And so I think no other power generation source has as much sort of public contention as nuclear power. And so I think some of those concerns are definitely pretty real. But from a safety perspective, there's a lot of drawn out fear that is not necessarily borne in the statistics. It's because nuclear energy has a pretty strong sort of connotation with nuclear bombs, and that can cause, I think, the public to to worry a little bit more, particularly about this type of energy source. Okay, so I noticed that we are at about half time now, and so we're going to take a break for 5 minutes. There are still a number of slides to go through, but actually what I think I'm going to do is instead we're going to hold off on those slides. I can cover that, I can finish them up next lecture, which will happen next week. And for the rest of lecture, I'm going to both go through the practice exam and then take any review questions that folks may have before the midterm. So let's do a quick break and I will get prepared for the practice exam. So there's a question. This has come up a couple times. Will the material we just covered be on the midterm? So no, we're only covering up to the last lecture. So last Wednesday, all the renewable stuff. So nuclear is not going to be on the midterm. Okay, let's go ahead and get started. Actually, before I dive into the first problem, I think that there's been enough questions from students, and concerns about both on the homework and with problems like this, that I want to clear up a little bit of confusion I think that there is between one of the more particularly confusing energy conversions. So between kilowatt hours and kilowatts, or more generally just watts versus watt hours. So kilowatts is a unit of power, whereas kilowatt hours is a unit of energy. So you can think of this as analogous to units of joules. And so when you are being asked to convert from kilowatts to kilowatt hours, you have to know, or even vice versa, you have to know how long or what time period you are operating for the kilowatts, right? Because it's essentially, something that is providing power or requiring power, and you need to know how long it is providing the power or how long it is asking for the power in order to determine the total amount of energy or electricity that it is either producing or providing. Okay, so as a really brief example, if I have let's say a 100 megawatt plant, and I want to know how much energy it's producing, I need to know over what period of time. And so 1 megawatt for 1 hour produces 100 megawatt hours of electricity. Okay. And if I were to do instead, say 1 year, if this was a power plant and it's producing 100 megawatts over the entire year, then it would be 1 year times 8,760 hours in 1 year. I just happen to know that off the top of my head, times 100 megawatts. So that would be 876,000 megawatt hours, right? Because I know that the time period here. And if instead it were for 1 second, there are, in 1 hour, there are 3,600 seconds times 100 megawatts. So the number of megawatt hours here would be 100 over 3,600 megawatt hours. Okay, so just keep in mind conceptually that to go in between power and energy, you need to know a unit of time. Okay, and if you are sort of really astute about this, it makes sense from a unit perspective, because like a kilowatt is equal to a kilojoule per second. And so when you go to kilowatt hour, it's equal to kilojoule times hour per second. And these can actually cancel out. All right, and so then you're in units of energy, whereas per amount of time, you're in unit of power. Okay, so knowing that, let's go ahead and work on problem 1. Okay. So the peak electricity demand in the state of California is 50 gigawatts. Okay, so immediately I know I'm working in units of power because it's in gigawatts. And so if the state were to operate at this demand over an entire year, how much energy would be consumed? Okay, and in this case, this is exactly like the example that I just showed. So we are operating for 1 year. And so I can multiply by 8,760 hours per year. And I just multiply by 50 gigawatts. And so this is equal to 438 gigawatt hours, which is approximately 4.4 E5 gigawatt hours. Great. And then I can convert that to gigajoules, and that's just a simple unit conversion. So that would be 438,000 gigawatt hours times 3,600 gigajoules per gigawatt hour. And that is, okay, with the with sig figs, if I do about 2, it'll be about 1.6 times 10 to the 9th gigajoules. Okay. I'll also mention that the solutions for the practice midterm I'll just post after class so that you'll have some reference material. Okay. Suppose that all of the energy were supplied by biomass. How much would be required to meet California's demand? Okay, so the answer, the final answer from last time in gigajoules, it's 1.6 e to the 9. It's actually 15768 times 10 to the 9th gigajoules. I'm gonna preserve my my digits when I'm doing the calculation, and then I'll be able to do the rounding for the sig figs later. So here I'll just write 1.5768 times 10 to the 9th gigajoules multiplied by 0.35. Okay, so where is this number coming from? In the reference sheet, I need to convert from electricity to biomass. Okay, so as we know, you always lose energy in your energy efficiency conversion. Oops, so this should be divide, not multiply. So if I go up to my reference, I'm turning biomass into electricity with an efficiency of 35%. So I'm going to need, let me line this back up here. So I'm going to need more, energy than the biomass energy, because you lose energy from going from from biomass to electricity. So if this is the electricity that I need, the biomass energy will be larger, which means I need to divide by a number less than 1 so that it's a larger number. And then it's a matter of doing the unit conversion, which is 1 ton per 18 gigajoules, which is another number that's provided in the reference. So my gigajoules will cancel out and I'll be left with tons. And so this is equal to 250,285,714 tons, which is about 2.5 e to the 8th tons. Okay. So let's continue onwards. Make some more white space. So instead, suppose that all of the energy were supplied by solar power. How much primary sunlight energy would be required to meet California's demand? So again, we're going to start with our electricity energy, 1.5768 e to the ninth. So this is in gigajoules. We're going to do a conversion to electricity using the efficiency factor provided in the reference. So whereas biomass was at 35% efficiency, solar is at 15% efficiency. And that's all we need. So if I do this, it'll be 1.0512 e to the times 10 to the 10th gigajoules. So that is approximately 1.1 E10 gigajoules. And quickly, just kind of fact checking, right? So it's 10 to the 9th gigajoules of electricity and 10 to the 10th gigajoules of solar energy, which is exactly what we want, right? Because the conversion to electricity, again, loses energy because it's not perfectly efficient. And so we would expect that this number is larger than this number, which is what we find. So we're good to go. Great. So hopefully you guys are continuing to follow along here. Oops. Let's make some white space for part D. Okay, so which energy source requires more land to supply California's energy needs? Okay, so this is kind of similar to the homework, more unit conversion. I can take the biomass tons that I got from parts B and C. Okay, so how strict will you be? There's a question in the chat. How strict will you be with significant figures on the exam? Like if we list 1.0512. So there will, I'll probably, so if you ignore the sig figs and you just provide the example, you know, that's, I guess I care more about demonstrating the concept, but I'll probably mark off like 1 point for sig figs, but not more than say, 5 points for the entire midterm. So in the example given in chat, I guess they're asking 1.0512 E10 versus 10.512 0.00000. So these in theory are the same sig figs. So it's a matter of like precision in that I report out to this many digits because I'm fairly certain that these digits are what they are. That's what sig figs are. So the more digits that you're providing, you know, again, I said the zeros here are probably a little bit blurry. I would consider these to be essentially 5 significant digits, similar to this. So that's why I'm saying these are essentially the same. The reporting is more, so this is 5 sig figs, and then if I were to do 1.1 e to the 10, this would be 2 sig figs. So hopefully the distinction between these guys is clear, between 5 and 2. And the reason why you choose 2 significant digits is because I'm saying 50 here. And so there's only 2 digits being provided. If I wanted 5 significant digits, I would say 50.000. And then you would have more confidence to report that answer with more digits. Okay, so for biomass, it is 250, 285, 714 tons times 1 hectare per 15 tons times 10,000 meters squared per hectare. And this is about 1.7 E11 meters squared. Whereas for solar, we have 50 gigawatts. So the reason why I'm doing the gigawatts is because the reporting for the amount of land is by watts, which is a power unit, not an energy unit. And so I'm using the original 50 gigawatts divided by 0.15 to get the amount of solar energy or solar power to provide that amount of solar electricity. And then I multiply by 10 to the 9th watts per gigawatt times 1 meter squared per 200 watts. And that is about equal to 1.7 times 10 to the 9th meter squared, or yeah, also 1.7 E9 meter squared. So you can actually see here that you would need 100 times more land of biomass energy to provide the same amount of solar power. Okie doke. There are no questions there. We can continue on here. So 2 is more sort of unit conversion. How many miles are driven across the entire population of California? So actually here, I'm not actually providing the population of California. And so, you know, I'll probably do this on the midterm as well, where we'll leave some stuff that's ambiguous, where you can look it up, which is totally fine as long as you state your assumptions, right? And so I'm, again, like I was saying, there are some reference materials that I provided in the lecture slides that I'm providing in the midterm, but as long as you're using reasonable assumptions, you are welcome to use them, even if the numbers are different from what I'm providing. I won't mark points off as long as you've cited your sources. And actually here there was I think a question that had come up from students where they're saying, well, you know, should I be doing the entire population, which is actually how I answered the question, but some students pointed out pretty astutely that it probably makes more sense to do it by the number of vehicles, right? Because it's the average car that goes 12,000 miles a year. It's not the average, you know, person. So those are the types of things that I would be flexible with. So if you had here, instead of 40 million people, you use the 27 million cars, that would be totally okay. But anyways, sort of doing it the way I had approached the problem. So 40 million, so 12,000 miles per person, even though it's per vehicle technically. I multiply by 40 million people. in California, and that's equal to 4.8 E11 miles in total. And then in part B, if the average car has a fuel efficiency of 25 miles per gallon, how many gallons of gasoline are consumed per year? So here we know that there's 4.8 E11 miles, and we know that the average fuel efficiency is 25 miles, so I can calculate the amount of fuel consumed like so. And so this would be 1.92 E10 gallons, which is about 1.9. Okay. What are the carbon emissions associated with all the gallons of gasoline consumed? So now I continue on 1.92 E10 gallons, and then there is a conversion for emissions rate. This is actually the official EPA number that gets used federally to calculate emissions from gasoline. So it's 8,887 grams of CO2 per gallon, and that is equal to 1.706 E14 grams of CO2, which is about equal to 1.7 E14 grams of CO2. So that would be on the order of, let's see, if I go just as a quick sense, so that's equivalent to 1.7 times 10 to the 8th tons of CO2, and that would be equal to, I believe that's 170 million tons of CO2 per year in California. So quick and rough way of getting that estimation, but this number is fine to report. There's a question, would we be given a value like grams of CO2 per gallon on the exam? So yeah, I actually did provide that in this one, emissions rates here. And actually this for the next part of the problem as well, for the emissions rate of the California grid. But that's something that you can definitely look up yourself. And if there's a slightly different number, you can just cite the source. Okay, so in this part, we're saying, okay, what if we replace all the cars in part C with electric vehicles? What's the difference in emissions? Okay, so we go back to our miles, 4.8 E11 miles, and we multiply by the efficiency, which is provided here, 30 kilowatt hours per 100 miles. And again, you just make sure your units are canceling out, times, and then this number was provided in the emissions rate, 250 grams of CO2 per kilowatt hour. Cancel those out, and that gives a total of 3.6 E13 grams of CO2. And so the difference between those two, so this is the answer in part C, minus the electricity vehicle emissions, equals 1.34 E14 grams of CO2. So if you switched all the cars in California to electric, you would be saving something like 134 million tons per year in California. Nothing to sneeze at there. Okay. So I'm sort of just blasting through these problems right now. But in the meantime, you know, if any of you guys have questions about the topic that we're covering more generally, you know, you can feel free to type it out in chat or chime in. We don't need to sort of separate the practice midterm from the discussion of the concept. So if there are things about energy conversion that you are confused about, I'm more than happy to discuss that as we go through at the same time. Yeah, okay. Just to be clear, only lectures 1 through 8 will be on the midterm. Yes, that is correct. Question about the unit of the amount of CO2 should be grams or tons. Yeah, don't care either way is fine. To me, you know, reporting reporting the grams or tons, those are equivalent units of mass as long as you have the right answer. It doesn't really matter. I guess in theory, you could be doing wild conversions into random things, which I probably wouldn't appreciate, but would technically still be correct. So that you wouldn't lose any points for reporting one type of unit versus another. Yeah. Okay, so 3A is a question, is more of a conceptual question, improving which step would provide the greatest benefit to system pathway efficiency. So this harkens back to, I think, one of the earliest lectures where we talked about, there was that example of using a coal plant to provide power for a light bulb. And if you remember, anytime you improve the efficiency of a particular step, wherever it is, it will subsequently affect the amount of energy needed in all previous steps, right? And so what I mean is, suppose I were to improve the efficiency of the coal going to electricity. So the output of the coal electric plant, which is electricity. So if this efficiency process could be improved, that means that to get the same amount of energy I would need in steps prior to my efficiency improvement, I would need less energy here, and I would need less energy here, and I would need less energy here, right? Because again, if I want 1 unit of energy at the end, if I start at 2.8 at this step, then any improvement in the efficiency means that to get 1 exajoule, I subsequently need less energy in the prior steps. Okay, I see a question. Those numbers are the energy used during that process or the energy left in that stage? Good question. That is the amount of energy left. So yeah. So going from here to here means you started with 8.96 exajoules of coal, and you end up with 2.82, so 8.96 exajoules of coal going to 2.82 exajoules of electricity. Yeah. And so when I improve any particular step, again, the energy requirements at every prior step is decreased, which means that if I were to improve the efficiency in the final step, that affects everything downstream of it. Whereas if I were to improve the efficiency up farther, it would only improve there, everything prior to that. And so the best step to provide the greatest system benefit is the final step. Okay, so you can review this concept in, I believe, lectures 1 and 2. Okay. Now let's think about problem B. Suppose the energy use in electric vehicles from the charging point were improved from 2.53 going to 1 to 2.53 going to 2. So you are improving the efficiency. Compare that to an improvement from 8.96 to 2.82 to 8.96 to 5.82. So the first one is a 1 exajoule improvement. The other one is a 3 exajoule improvement, but it's farther along, right, in the stage. And so you're getting less overall pathway efficiency. So which one is better? So we can do the math to figure that out. Oh, okay. So I see a question. What calculation gives the pathway efficiency of 9.9%? So the total efficiency of the pathway is final energy divided by starting energy, right? This is like what I get out versus what I put in is my efficiency. And so this, in this particular case, is 1 exajoule, which is my final, divided by 10.1 exajoules, which is my starting. And that's going to give me about 9.9%. Yeah, so like that and like that. Okay. So the first improvement is I'm actually just going to go ahead and do the same thing, right? So we're talking about calculating the greatest benefit to this system pathway efficiency. So we want to get this final number for this improvement and for this improvement. So first improvement is so I'm ending up with 2 exajoules. So 2 exajoules divided by 10.1 exajoules, which is equal to 0.198. So about double efficiency, right, from 9.9%. Then the second improvement is a little bit trickier. I want to get an understanding of if I changed, so these numbers all stay the same up until here, and this gets changed to 5.82, and the efficiency of each of these subsequent steps stays the same, right? And so I can calculate the efficiency of those steps by doing the individual step would be, 2.53 over 2.82 2.82, which is the efficiency of this step, and then 1 divided by 2.53, which is the efficiency of this step. So the way I would calculate this would be, let's see, 5.82 going through the same efficiency cycles, which is times 2.53 divided by 2.82 times 1 over 2.53, which should give me the final energy that I have left. And so this will be approximately 2.06 exajoules. Okay, and so now I can just do the simple formula that I did here. Instead of 2, it's 2.06 over 10.1 exajoules. And that is equal to 0.204. Okay, when I compare these two numbers, I can say the second is more efficient. Okay. So in this case, I think that this problem is, if you're getting a sort of firm grasp of the efficiency concepts, I think that this should be pretty straightforward. Essentially, you're changing individual efficiencies at different points, and you are then recalculating your total system pathway efficiency. Okay. So now let's move on to problem 4. Okay, so this one is another one of the problems where I want to clarify concepts a little bit. I think that there were some requests and some confusion here thinking about what the concept of present value means. Okay. So as we recall from our lecture on economics and financing, energy economics and energy financing, there's this concept that like the time value of money is different over time. Just kind of put yourself in this position where you're thinking about, suppose you are lending someone money, or you are making a decision about whether or not to take money. If you are lending someone money, say you give someone $1,000 and they repay you, $100 every year for a decade. Well, okay, after 10 years, you end up getting all your money back, right? But it seems kind of a bad deal, because while you get the $1,000 back, the value of the money 10 years from now is worth less than it is today. Right, because I could have used that money for other things rather than having to wait a long time to get access to it. And so the same concept applies to, you know, receiving money. I would rather receive money today than a year from now because I can use it to like invest, and then at the very least I could put that away into like a bank, for example, and a year from now I would at least have whatever interest that I made. And that whole concept is called discounting, and that is relating to the present value of the money. And essentially what I'm doing is I'm figuring out how I value money at over different periods of time, which is the discount rate, to see how much it's worth to me, how much future money is worth to me now, or how much money today is worth in the future. So there's this whole thing of this 1 plus I, or sometimes R to the N, which I think most of you are familiar with at this point. And there's a question of like, how do I apply it? Because it can actually go different ways, right? You can do, you know, value times this. You can also do value divided by 1 plus I to the N. So rather than like write out this specific equation for you to memorize, I think the best way to think about this is to use your logic about how much money is worth now versus the future. Okay, so this quantity here is going to be, say, if it's like a 10% discount rate, 1.1 to some thing. So when you multiply by a number larger than 1, that will increase your value, right? If you divide by a number that's larger than 1, that will decrease your value. So if I am looking for how much, like a future value, say $1,000 10 years from now is worth today, it is worth less. Okay, and because it is worth less, I need my value to decrease, so I'm going to divide. If I am looking at value that needs to be increasing, right? So if I have money that needs to be paying interest, for example, you can do that calculation by multiplying, because I know that I have to pay more money in the future. And so that would be using something like this. So instead of memorizing future value, present value equations and all that, just think about whether or not the money is going to be more or less in the time period, in the time frame you're considering, and then you can multiply if it's more and divide if it's supposed to be less. Okay, and so hopefully that clarifies some of the confusion about the present values. But let's talk about this specific problem. So that we can clear this up through an example as well. So how many kilowatt hours of electricity are generated? So we know that it's 300 megawatts. It has a capacity factor of 80%, so times 0.8, meaning that it doesn't operate at a full 300 megawatts every year. It's at 80% of that. We will multiply by 1,000 kilowatts per megawatt, and then 8760 hours per year. So this is, so in 1 year, this is the rate at we're going, and it's 8760 per year. Okay. And so this is equal to 0.2102, 400,000 kilowatt hours per year, which is about 2.1 e to the 9 kilowatt hours per year. So we'll store this number away for later, which we'll need for the levelized cost. Okay, how many gigajoules of natural gas are used? So we know all the conversion efficiencies. So if we start at our 2.102 E9 kilowatt hours per year, we can multiply by 277.8 kilowatt hours per gigajoule. And then we also have to take into account the efficiency, right? And so it's 1 divided by 0.55. And that will give us the gigajoules of natural gas, which is about 13.76 E6 gigajoules per year. Okay. For the CRF, we know the equation is equal to I over 1 minus 1 plus I to the negative n, which is equal to 0.1 over 1 minus 1.1 to the negative 25, and that's equal to 0.1102. Okay, approximately 0.11. I know I'm kind of blazing through this pretty quickly because we're nearing the end of class time, but again, the answers and the work will be posted shortly after class today, so you will have time to review at your leisure. So what is the levelized cost of electricity if natural gas costs $3 per gigajoule? Okay, so there's a bit to calculate here. So we know CRF is equal to 0.1102. We know the capital cost is equal to 300 million. And we know the kilowatt hours is equal to 2.102 e to the 9th kilowatt hours per year. The O&M is equal to $10 million per year. Okay, so the first thing we need to do is to get the annual cost of natural gas. So this follows right along with the homework. So that's equal to 13.76 gigajoules, which we calculated in part C, times $3 per gigajoule. And so that's about equal to $41.3 million per year. So this is fixed. So the total O&M is about $51 million a year, which is the sum of these two. And so the levelized cost, LCOE, is equal to the CRF times CC plus all my annualized costs, annual costs, divided by the total amount of electricity, and so this is just this number times this number plus the 51 sum. Okay, and the electricity we know from here, and we can just divide, and this ends up being about equal to 4 cents per kilowatt hour. Okay. So I am gonna stop here because we've run out of time for today. But I will again post the answers, and you can see the rest of the solutions to the practice midterm online. There's a question: has assignment 1 been graded? So Facundo is still working on that, but the solutions for homework 1 have been put up, and so you should be able to access that under Canvas files, and that would also be good review material for the midterm. Yeah, and there's an announcement on Canvas that points out that location as well. Yeah, so there's another question. Annual cost is the sum of O&M and the natural gas cost per year. That's right. So think about this kind of logically. You buy the power plant, and that's the capital cost, and then the annual cost after sort of purchasing the power plant is just all the operations and maintenance. So you have to pay the workers, and then you have to pay any fixed operations and maintenance related to repairing any equipment. So that's all of that number is built into the fixed O&M, and then the other part of the annual cost is whatever fuel costs that you need to pay for the production of electricity. So adding up, that's generally how it is. The components of cost. You've got your capital cost, which is not an annualized cost, but you can calculate the annualized cost. And then you've got your annual costs, which are your operations and maintenance and your fuel costs. And you can just add those up, and that gives you your total annual costs. Okay, great. We'll end here for today. Good luck on the midterm on Wednesday. That'll be, again, getting posted 10 a.m. And it'll be due 10 p.m. on Thursday. I'll stick around for any last minute questions from students for a couple minutes.